The objective of this lecture is to provide the fundamental concepts in kinematics of a rigid body. This lecture will be divided into the following parts. First, a definition of a rigid body is provided. Next, the kinematics that relate velocity and acceleration between 2 points on a rigid body are developed. And then third, an example that uses these kinematics is given. And then fourth, the kinematics of rolling and sliding are discussed. And then finally, an example of rolling is provided. So let's start with the definition of a rigid body. So a rigid body denoted generically by the symbol B is a collection of at least 3 non-collinear points whose distance from one another is constant. Now, going back to earlier lectures on kinematics, that definition should seem somewhat familiar in that a reference frame is also defined as a collection of at least 3 non-collinear points whose distance from one another is constant. The only difference between a rigid body and a reference frame is a reference frame is a purely mathematical construct, whereas a rigid body may actually have mass or may have inertia. Now, we're not considering the mass of the rigid body or the inertia of the rigid body at this point. So from the standpoint of kinematics, it's equivalent to say rigid body or say reference frame. So I'm going to write that down, which is kinematically saying a rigid body is equivalent to a reference frame. So that means B is a rigid body is the same thing as saying B is a reference frame. Now, given that definition, suppose that we have an arbitrary reference frame A. I'm going to say let A be an arbitrary reference frame. Then, because B is also a reference frame, B has an angular velocity relative to A. So we can say that omega BA is equal to the angular velocity of B relative to A. Now we can use the fact that B is a reference frame and it moves or rotates relative to A to be able to define the next part, which is the velocity and acceleration between 2 points on the rigid body. So now let's start with the following picture. Suppose that B is my rigid body and I depict it as shown, and I have 2 points. I'm going to call those points Q and P. Now there's a vector that connects Q to P, and that's the position of P relative to Q. So the position of P relative to Q is denoted RP/Q. So this is the position of P relative to Q. Now suppose, we're going to make this assumption, assume that P and Q are fixed in B. So this is an important assumption. So if P and Q are fixed in B, then that means that the vector from Q to P also has to be fixed in B. So because P and Q are fixed in B, that implies that the position of P relative to Q is also fixed in B. And when a vector is fixed in a reference frame, that implies that the rate of change in that reference frame of that vector has to equal 0. So that's the first part of this derivation of the velocity between 2 points in a rigid body. Now let's suppose that I have a reference frame. I'm just going to arbitrarily call this frame A. As I said, A is some arbitrary reference frame. And we're going to also assume that B rotates relative to A. So B rotates relative to A. And that implies that omega BA is the angular velocity. Of B relative to A. Now, given that I have that angular velocity of B relative to A, and I know the rate of change of the position of P relative to Q in frame B, I can now compute the position of P relative to Q in frame A by applying the transport theorem. So then, applying the transport theorem, from B to A gives that the rate of change of the position of P relative to Q in frame A is equal to the rate of change of the position of P relative to Q in B plus omega BA crossed with the position of P relative to Q. But we already derived that the position of p relative to q in B is 0. So that implies that the rate of change in A of the position of p relative to q is equal to omega BA crossed with the position of p relative to q. But the rate of change of the position of p relative to q in A, that is equal to the velocity of p relative to q in A. So we know that the velocity of p relative to q in A is equal to the rate of change in A of the position of p relative to q, which implies that the velocity of p relative to q in A is equal to the angular velocity of B in A crossed with the position of p relative to q. Now we can either write it that way, but sometimes, just to be a little bit more explicit, it's actually written as the difference between two velocities. So we can equivalently write this as the velocity of p as viewed by an observer in A minus the velocity of q as viewed by an observer in A is equal to the angular velocity of B in A crossed with the position of p minus the position of q. Either way, it's the same thing. The first one's a little bit more compact, but it's a little bit more implicit. The second one is less compact, but it's more explicit. So that gives us the velocity between 2 points on a rigid body. So using this result, this difference in velocity between 2 points on a rigid body, we can now apply the transport theorem a second time to be able to compute the acceleration of p relative to q in A. So we have that the acceleration of p relative to q in A is equal to the rate of change in A of the velocity of p relative to q in A, which is equal to the rate of change in reference frame A of the angular velocity of B in A crossed with the position of p relative to q, where we note that we've just substituted the first result into this second rate of change in order to be able to obtain the acceleration of p relative to q in A. Now let's expand this last expression to be able to get the final result for the acceleration of p relative to q in A. So then, the acceleration of p relative to q in A is equal to the rate of change in reference frame A of the angular velocity of B in A crossed with the position of p relative to q, which, if we expand this into two terms using the product rule, for differentiation, we've got d dt in A of omega BA crossed with the position of p relative to q. That's the first term from the product rule. And the second term from the product rule is omega BA crossed with d dt in A of the position of p relative to q. So now we know that the angular acceleration of B in A is equal to d dt in A of omega BA, which is also equal to d dt in B of omega BA. And that's from the transport theorem again, that d dt in A of omega BA is equal to d dt in B of omega BA, because the second term in the transport theorem is then omega BA crossed with omega BA, which is 0. So that is the angular acceleration. So I could substitute this expression for d dt in A of omega BA into the previous expression and just use alpha, which is the angular acceleration. So this is the angular acceleration of reference frame B relative to reference frame A. So it's the second term that's actually a little bit more complicated. So the second term, we have that d dt in A of the position of P relative to Q. Well, we have that from the previous result. That's equal to omega BA crossed with the position of P relative to Q. So now we can substitute all of that into this expression for the acceleration of P relative to Q in A, and we get alpha BA crossed with the position of P relative to Q plus omega BA crossed with omega BA crossed with the position of P relative to Q. Now, you'll notice that in both these expressions, so let's put these expressions alongside one another so we can actually see them, that the difference in velocity and the difference in the acceleration. So then, the velocity of P relative to Q in A is equal to the angular velocity of B in A crossed with the position of P relative to Q, and the acceleration of P relative to Q in A is equal to the angular acceleration of B in A crossed with the position of P relative to Q plus the angular velocity of B in A crossed with the angular velocity of B in A crossed with the position of P relative to Q. Now you'll notice that in order to be able to compute the difference in velocity between 2 points on a rigid body and the difference in acceleration, the information that's needed is how the body rotates, which is obtained from the angular velocity of B and A, and how the rotation of the body changes, or the rotation rate of the body changes, which is the angular acceleration of B and A. And the only other thing we need is we need the difference in the position between the 2 points. So once we know everything about the first and second rotation rates, if you want to call it that, or angular velocity and angular acceleration, and we know the difference in position, we can fully characterize the difference between the velocity and the acceleration of 2 points on a rigid body. So this is the basic construct of kinematics that's used over and over again in order to be able to solve rigid body mechanics problems. So as I said, we're going to be doing examples throughout this lecture. So let's do one example right now, a simple example, just to be able to show what's going on. So consider the following problem. Which is I have an arm that rotates in the plane, and attached to it is another arm. And I'm going to call the hinge point of the first arm, I'm going to call it O. The hinge point between the two arms, Q, and the tip of the second arm, P. And the angle that's formed between the vertically downward direction, if you want to call it that, and the first arm, I'm going to call that theta 1. And the angle between the first arm and the second arm is going to be called theta 2. And I'm just going to label these two lengths of these arms as L1 and L2. So now I have a two linkage system. So what I'm going to actually do in this problem is, because the previous result was to get the difference between the velocity and acceleration between 2 points on a rigid body, in this problem, the objective is going to be to obtain the velocity of P relative to Q as viewed by an observer fixed to the ground, and then I'm going to do the same thing for the acceleration of P relative to Q. So the objective is determine the velocity and acceleration of point P relative to point Q as viewed by an observer fixed to the ground. And the ground is just going to be abstractly labeled out here as G, which is the ground. So now, in order to be able to do this problem, we have to do this the same way we do all kinematics problems, which is we need to determine the number of rotations and we need to determine the number of frames as a result of that. So the solution to this problem is going to follow the same process that was outlined in regular kinematics. It's just things are going to simplify because the distances between these points are constant. So now, to start the solution, we have to know the number of rotations. So the number of rotations is equal to 2, which implies the number of reference frames that are needed is equal to 3. And without spending too much time on reference frames this time around, we have 3 frames. So the 3 frames are the frame of the second arm, the frame of the first arm, and the frame of the ground. So I'm going to call G the ground. A is going to equal the first arm. And B is the second arm. Now you'll notice in this problem, points Q and P are both fixed in B because they're fixed in the second arm. So that means that we need to express everything in coordinates fixed in the second arm. So let's write down now the 3 coordinate systems that are associated with these 3 frames, working our way backward, which is we're going to start with B, which is the second arm. The coordinates that are going to be fixed in this frame, the origin of this coordinate system is going to be at Q, because remember, the origin of the coordinate system has to be fixed in the reference frame in which we're describing. We're describing the reference frame, which is the second arm, so the origin of the coordinate system has to be fixed in the second arm. And then what I'm going to do is I'm going to put U1 is going to be along QP, and then U3 is going to be out of the page, and then U2 is equal to U3 crossed with U1. So that's the second arm. Now we're going to do A, which is the first arm, and this coordinate system is going to have its origin at O. So O is fixed to the first arm. Q is also fixed to the first arm, but we can't really measure distances from point Q because it's the end of the first arm. So we have to measure from another point that's fixed in the first arm. The only other point we have is O. And then I'm going to put E1 is going to be along OQ, and E3 will be the same thing as U3, and E2 will equal E3 crossed with E1. And then the last frame, or the first frame in this case, is the ground. And the origin here is also going to be at O. And then I'm going to just pick 3 vectors. I'll call them E1, E2, and E3 are going to equal little e1, little e2, little e3 when theta 1 equals 0. Now the vector of interest in this problem is the position of P relative to Q, because the objective is to determine the velocity of P relative to Q in G and the acceleration of P relative to Q in G. But note that the position of P relative to Q is equal to L2 times U1. And this vector is expressed in coordinates fixed in reference frame B. So because it's expressed in coordinates fixed in reference frame B, the results that have been derived for kinematics of a rigid body have to be applied using the angular velocity of B and G and using the angular acceleration of B and G. So that's what we're going to do next. So given that the position of P relative to Q is expressed in coordinates fixed in B, and the objective is to determine the velocity of P relative to Q in G and the acceleration of P relative to Q in G, it is necessary to determine the angular velocity of B in G and the angular acceleration of B in G. Now, why is it that we need those? And that's because of the following. The velocity of P relative to Q in G is equal to the angular velocity of B in G crossed with the position of P relative to Q. And the angular acceleration of P relative to Q in G is equal to the angular acceleration of B in G crossed with the position of P relative to Q plus the angular velocity of B in G crossed with the angular velocity of B in G crossed with the position of P relative to Q. So you can see that I need the angular velocity of B in G and the angular acceleration of B in G. So the angular velocity of B in G is equal to the angular velocity of A in G plus the angular velocity of B in A. Now, A rotates relative to G by an amount theta 1, and the angular rate is theta 1 dot, and the direction is the direction E3. So this is equal to theta 1 dot E3. And then B rotates relative to A with an angle theta 2, so its angular rate is theta 2 dot, and it's in the direction U3. Now, of course, in this particular case, E3 and U3 are the same. So because E3 equals U3, that implies that the angular velocity of B in G is equal to theta 1 dot plus theta 2 dot times U3. Now notice I've expressed everything in coordinates fixed in B. I could have used E3 because it's the same thing as U3, but I want to use U3 because U3 is the vector, the third basis vector associated with the basis that's fixed in reference frame B. And even though mathematically it's equivalent to E3, everything needs to be expressed in that basis, U1, U2, U3, because that's the basis I chose that's fixed in reference frame B. So now I have the angular velocity of B and G. So then the angular acceleration of B and G is equal to the rate of change in reference frame B of the angular velocity of B and G, which is equal to theta 1 double dot plus theta 2 double dot times u3. So now I have everything I need in order to be able to compute the velocity and acceleration of P relative to Q in reference frame B. So let's do this sequentially. So first, the velocity of P relative to Q in G is equal to, let's write it first and then is omega bg crossed with the position of P relative to Q. Now I can substitute, which gives me theta 1 dot plus theta 2 dot u3 crossed with L2 times u1. So now I can simplify this. u3 crossed with u1 is u2. So now I can use that to be able to compute the the velocity of P relative to Q in G. So therefore, the velocity of P relative to Q in G is equal to L2 times theta 1 dot plus theta 2 dot times u2. So that takes care of the velocity of P relative to Q and G. So next, the acceleration of P relative to Q and G is equal to alpha bg crossed with the position of P relative to Q plus omega bg crossed with omega bg crossed with the position of P relative to Q. Now I know I already wrote that, but I'm writing it again because I'm just trying to reinforce that these are the concepts that we have to use over and over again. So this expression that I have here, now if I substitute everything in, you get theta 1 double dot plus theta 2 double dot times u3 crossed with L2 times u1 plus theta 1 dot plus theta 2 dot times u3 crossed with theta 1 dot plus theta 2 dot times u3 crossed with L2 times u1. So let's go through all of these vector products. u3 crossed with u1 is again still u2. So this gives me L2 times theta 1 double dot plus theta 2 double dot times u2. And now let's go through this next set of cross products. So u3 crossed with u1 is u2. And then the result of that, I'm going to take the cross product of u3 with that. So u3 crossed with u2 is minus u1. So this gives minus L2 times theta 1 dot plus theta 2 dot squared times u1, which I can of course put back in the order of the basis, which is u1, u2, u3, and that gives minus L2 times theta 1 dot plus theta 2 dot squared plus L2 times theta 1 double dot plus theta 2 double dot times u2. So that's the result for this problem. This first expression on this page is the velocity of P relative to Q and G. The second expression is the acceleration of P relative to Q and G. And you'll notice that both expressions are fixed or expressed in coordinates fixed in reference frame B. So you can think of B in this case as being that rigid body that I had defined abstractly before when I did the theory. Because that's the body that I'm actually interested in its motion, and I'm interested in how points move relative to one another on that body. But that body, of course, is rotating relative to another body, and that body is rotating relative to the ground. So this problem was more complicated, but the kinematics still follow the same principles, which is that you have to add angular velocities, and then you have to express everything in the coordinates that are fixed in the last frame that's rotating, which in this case is the frame of the rigid body. So everything's always expressed when you're doing rigid body kinematics in terms of the reference frame that's fixed in the last body, which is the rigid body, and it's the body of interest. So the next concept, which adds on to the previous concept, is that of rolling and sliding. Now, rolling and sliding are a bit confusing, but the way rolling and sliding is done, it's actually a very simple result, but it's not that easy necessarily to understand it until you take a little bit of time to think about it. So suppose that B and S are two rigid bodies. And also, suppose that the surfaces of B and S are described by smooth functions. What that basically just means is that these are not rough surfaces; they're smooth. You can think of them as being like a smooth curve. And here's the key point to this derivation, or this concept that I'm about to expand upon, which is that let B be moving such that B is in continuous contact with S. So here's what this picture looks like. Here's B, and here's S. So this is B and this is S. And they're in contact with one another. So there's a point Q. I'm going to call that point Q. And Q is the point of contact between B and S. Now, Q is what's called the instantaneous point of contact. This is really important. Q is the instantaneous point of contact. And this is the part about rolling and sliding that is most confusing. Is that at one instant of time, there's a point between these two bodies that defines that point of contact, Q. But as B moves, because S may also be moving too, but it doesn't matter. They're moving relative to one another. That point of contact may be a different point of contact. So let's draw this in a diagram, and it's a little bit easier to see. So if I consider two instants of time, here's one instant of time, which is kind of schematically what I drew before, which is I have these two bodies. I've got B and I've got S, and I've got this point Q. But at a later point in time, B may have rotated into this configuration, and S may have rotated into this configuration, in which case this point Q here is not the same point as what it was earlier. So this you can think of this as at t equals t1, and you can consider this to be at t equals t2, and the point of contact has changed. So it's an instantaneous point of contact in that it only applies at that particular instant. So at time t equals t1, the point Q that's in contact with the between the two bodies is the point that's defined at that instant to be in contact, and that point changes as time evolves. That's a confusing concept, and it's understandably confusing, but the point of contact does change as the two bodies move relative to one another. So now, given that we've defined the instantaneous point of contact in this manner, we define two constructs, which are rolling and sliding. So the first thing is rolling. So we say, so B, or body B, is said to roll on body S instantaneously. Now this is really important. It's instantaneously. Instantaneously, if the following condition is met. And that condition is that the velocity of point Q on body B, as viewed by an observer in an arbitrary frame, is equal to the velocity of point Q on body S in an arbitrary frame. And again, A is just an arbitrary frame. It doesn't make a difference what A is. And this is true for all reference frames A. It doesn't matter what the frame is. This is the definition of rolling. Now, rolling, you could think of, what that means is that the instantaneous point of contact, whatever that is, the velocity, the relative velocity between the two objects at the instantaneous point of contact, that particular point on both bodies, is 0. So this is another way to say this. So rolling implies that the velocity of point Q on B is the same as the velocity of Q on S. So in other words, what we're saying is that the velocity of point Q on B in A minus the velocity of point Q on S in A is equal to 0. Now that's rolling. So rolling and sliding are kind of complementary things. So although this sounds somewhat trivial, sliding means that the velocity of point Q on B in A is not equal to the velocity of point Q on S in A. It's basically whatever rolling is not, that's sliding, because remember that we're dealing with a point of contact. If these two bodies were not in contact with one another, we wouldn't have any of this going on, but it's only going on because we're dealing with contact. Now, it's easier to actually deal with this in the form of an example because it often clears up the confusion that comes in with rolling. So let's suppose we have the following problem. Suppose I have a circular disc and it's rolling on a flat horizontal surface, which I'm just going to depict as the ground. And there's a point Q that is in contact with the two, on the disc. So I'm going to call this the disc and we'll call this the ground. So there's a point on the disc, and this, just to be complete about the picture, the disc has a radius capital R. Doesn't really matter, but it'll help the situation a little bit. Now, because Q is the instantaneous point of contact, so Q is the instantaneous point of contact between D and G. And now assume that D rolls on G. Well, then that implies that the velocity of point Q on D, as viewed by an observer fixed to the ground, has to equal the velocity of point Q on the ground as viewed by an observer fixed to the ground. But the velocity of point Q on the ground as viewed by an observer fixed to the ground has to equal 0 because the ground can't move relative to itself. So that implies that the velocity of point Q on the disk as viewed by an observer fixed to the ground has to equal 0. So this is somewhat of a trivial example, but now what we can do is we can add to it. So suppose the center of the disk is O. Now I'm going to add to this picture, and I'm going to compute the velocity of the center of the disk using this information, because now I have enough information to be able to do that. So in order to be able to do this more clearly, we're going to make this picture yet a little bit clearer in terms of the information that we put in this diagram to make it easier to be able to compute this, this velocity of point O. So here's a more complete diagram. Which is that, again, I have the disk. But now what I'm going to do is I'm going to take this point O, I'm going to put a point P on the edge of the disk. And I'm going to draw the line or the vector from O to P. And I'm going to say that this angle that's formed by the vertical with the direction OP, I'm going to call this angle theta. Now I'm going to put the ground back in the diagram. And here's point Q again. Now, let's look at something. Is that I'm going to put a coordinate system that is going to have its x direction to the right. And it's going to have its y direction down. And then I'm going to put EZ into the page. Now, this coordinate system is actually fixed to the ground. I have a coordinate system that's also fixed to the disk. I'm going to call this direction, I'm going to call it ER. I'm going to call this direction E theta. And then I'm going to say EZ is into the page. So now this problem has one rotation. So that implies that we need 2 reference frames. Well, I've just constructed 2 bases, so I have 2 reference frames. So let's start with the disk. All right, so D is equal to the disk because that's my last frame, right? And the origin of that coordinate system is going to be at O. And what I'm going to do is I'm going to put ER is going to be along OP. EZ is into the page. And then E theta is equal to EZ crossed with ER. The next frame is going to be the ground. Now this is a little bit trickier because I need an origin, right? O is fixed to the disk. O is the center of the disk, and that's not fixed to the ground. So I need a point that's fixed to the ground. So for lack of anything better, I'm going to say the origin is going to be at O when t equals 0, whatever that happens to be. And I'm going to also assume in this, just because it's going to make things a little bit easier, it's arbitrary, that theta is equal to 0 corresponds to t equals 0. I'm just going to say that they're the same thing. So that t equals 0 also corresponds to when theta is equal to 0. Then I'm going to put EX is going to be to the right. And EZ is the same as it was before. It's into the page. And then EY is equal to EZ crossed with EX. Now what I'm going to do is I'm going to use the fact that I just used the no slip condition, because this is the key thing, is there's no slip or there's no sliding at this point because it's rolling. So I'm going to use that fact to be able to compute the velocity of point O. So we know that instantaneously Q is a point on both the disk and the ground, because it's the instantaneous point of contact. So that means that instantaneously Q is a point on the disk. So we want the velocity of point O. So also the velocity of point O relative to Q as viewed by an observer fixed to the ground has to equal the angular velocity of the disk as viewed by an observer fixed to the ground crossed with the position of O relative to Q. And we can now get the velocity of O relative to Q. So the velocity of O relative to Q in G is equal to, well, what's the angular velocity of the disk as viewed by an observer fixed to the ground? It's equal to theta dot times EZ, into the page, EZ. And the position of O relative to Q is equal to minus R EY. So as a result, we get theta dot EZ crossed with minus R EY, which implies that the velocity of O relative to Q in G is equal to R theta dot EX. But notice something. Recall that the disk rolls without slip on the ground. So that implies that the velocity of point Q on the disk as viewed by an observer fixed to the ground has to equal the velocity of point Q on the ground as viewed by an observer fixed to the ground. But as we found out earlier, that's equal to 0. So expanding this last term, this is where the expansion actually is helpful, which is that the velocity of O relative to Q in G is equal to the velocity of O in G minus the velocity of Q in G. But the velocity of Q in G is 0 because Q is a point that's fixed to both the disk and the ground. So the second term over here is 0. So this just gives the velocity of O in G, which means that given that the velocity of O relative to Q in G is the same thing as the velocity of O in G, because Q is the instantaneous point of contact and the disk rolls without slip on the ground, this gives me that the velocity of O in G is equal to R theta dot EX. So that gives me the velocity. Now I have the velocity of point O as viewed by an observer fixed to the ground. So the last step now is to compute the acceleration of point O as viewed by an observer fixed to the ground. So let's do that next. So then the acceleration of point O as viewed by an observer fixed to the ground, well, that's actually much easier now than we could have actually imagined it to be, because the velocity of point O as viewed by an observer fixed to the ground is equal to R theta dot EX. But note, EX is fixed in G. So as a result, I can just take the derivative straight away, because when there's no transport or anything that's required, because EX is fixed in G, I'm taking the derivative as viewed by an observer fixed in G, and all I have to do is differentiate the coefficient. So as a result, I get that the acceleration of O in G is equal to r theta double dot times Ex. Now the last thing is to be able to compute the velocity and acceleration of P. And we can do that now using 2 points fixed in a rigid body. So suppose now that it is of interest to compute the velocity of point P in G and the acceleration of point P in G. Well, we know the velocity of P relative to O in G, because P and O are fixed in the disk. So P and O are fixed in D. So that implies that the velocity of P relative to O in G is equal to the angular velocity of the disk as viewed by an observer fixed to the ground crossed with the position of P relative to O. But we already have the angular velocity of the disk in the ground. The position of P relative to O is equal to R times ER, the way I defined it. So as a result, we get the velocity of P relative to O in G is equal to theta dot EZ crossed with RER, which is equal to R theta dot E theta. So then that implies that the velocity of point P in G is equal to the velocity of O in G plus the velocity of P relative to O in G, which is equal to R theta dot Ex plus R theta dot E theta. So finally, we can do the same thing for the acceleration of P relative to O and G. So finally, the acceleration of P relative to O and G is equal to the angular acceleration of D in G crossed with the position of P relative to O plus the angular velocity of D in G crossed with the angular velocity of D in G crossed with the position of P relative to O. So now we can just substitute everything again in here to be able to get the acceleration of P relative to O. So we then have that the angular acceleration of D in G is equal to theta double dot EZ, which of course is equal to the rate of change in D of the angular velocity of D in G. I'll just recall that just so that we know that that's what we're dealing with. So then the acceleration of P relative to O in G is equal to theta double dot EZ crossed with RER, because that's the position of P relative to O, plus theta dot EZ crossed with theta dot EZ crossed with RER, which is equal to R theta double dot E theta. And again, we take the cross product, EZ crossed with ER is E theta, and EZ crossed with E theta is minus ER, so we get minus R theta dot squared ER. And that's the acceleration of P relative to O in G. And we can just add the acceleration of O to get the acceleration of P. So this is equal to the acceleration of O in G plus the acceleration of P relative to O in G, which is equal to R theta double dot Ex. And then I'm going to put this in the right order. Get minus R theta dot squared ER plus R theta double dot E theta. So that is a full kinematic analysis on this disk of radius r rolling without slip on the ground. And we've computed the velocity of the point of contact relative to the ground, which is 0. We've then computed the velocity of the center of the disk, which is at point O, And then we computed the acceleration of the center of disk, again, all of this relative to the ground. And using that information together with the kinematics between point O and point P, which was the point on the edge of the disk, we were able to compute the velocity of P relative to O in G, and then the acceleration of P relative to O in G. And then we were able to add the velocity of O and the acceleration of O as viewed by an observer in G to finally get the velocity of P in G and the acceleration of P in G. So to summarize this lecture, first, a rigid body was defined. And then using that definition of a rigid body, the kinematics relating the velocity and acceleration between 2 points on a rigid body were derived. And then third, an example was provided that used these relationships that were derived. And then fourth, a discussion was provided of kinematics of rolling and sliding when a rigid body moves while in contact with another body, and then fifth, an example of rolling was provided. And the results obtained in this lecture will be used as the basis for further kinematics that will be developed for a rigid body, and then to be able to eventually develop kinetics of a rigid body, because all these results are needed for kinetics of a rigid body as well. But that will be the end of this particular lecture.